Hello, complex analysis students. So today we want to talk about several really big consequences of the Cauchy integral formula. The first one is called Liouville's theorem. It just says that if a function f is entire, which means analytic on the entire complex plane, and it's bounded on the entire complex plane, then really that function must have been a constant. In other words, only constant functions can have this property of being entire and bounded. Let's look at a proof of that real quick. It's surprisingly straightforward. Falls right out of some things that we've already proven. So let's start our proof just by assuming that f is entire. And when we say f is bounded, we just mean that the modulus of f of z is less than or equal to some non-negative constant. And this is, since it's a bound for the entire complex plane, this is true for every complex number z. Well, we had a corollary to the extended version of the Cauchy integral formula that applies here. That corollary is called Cauchy's inequality. This thing said that if you got a function that is analytic inside and on a circle of radius r centered at some point z naught, then all of the derivatives at z naught have this upper bound that looks like n factorial times whatever the bound of the function was on that disk divided by the radius of that circle to the nth power. If we apply that to this particular situation and use the first derivative version of it, and it applies to every size circle because, you know, it doesn't matter how big our circle is, it fits inside the complex plane. So for every r greater than 0 and for every z in the complex plane, we could look at a circular disk centered at arbitrary z of arbitrary r, and we would have the following inequality. Modulus of f prime of z has to be less than or equal to this upper bound m on the modulus of the function over r to the 1 in this case, since we're doing the first derivative. But r can be arbitrarily large, so that means that the modulus of f prime of z here must be equal to 0. Because if the modulus of f prime of z is less than any positive number, which it would be if r can go to infinity in that fraction, then yeah, this derivative must be 0 in modulus, and so that means that the derivative itself is equal to 0 without modulus. But then we had another result. This was way back when we were just introduced the idea of analytic functions. We had a theorem there that said if a function is analytic on a domain and the derivative is equal to 0 on that domain, then the function has to be constant on that domain. So by a previous theorem, since the derivative is equal to 0 on this domain, the function has to be constant on that domain. So f is constant on the whole complex plane, which is the result we wanted. So that was pretty quick and tidy proof of Liouville's theorem. It's kind of surprising. I mean, it certainly doesn't have an analog in the real numbers. You can have a function that's differentiable on the whole real number line, and it can be bounded, but it doesn't mean it has to be constant. You know, just take a function that, you know, has a horizontal asymptote. It could be perfectly differentiable, and so yeah, this result is unique to the complex numbers. And we can use it to prove what's called the Fundamental Theorem of Algebra, which you may be familiar with from like some pre-calculus level class. It just says if you got a polynomial that has degree n, so that just means that your leading coefficient here is not equal to 0, then it has to have at least one number that you can plug into it that makes it equal to 0. In other words, it has to have at least one 0. So let's prove that. And we'll prove this by proceeding indirectly. So let's suppose to the contrary that p of z does not equal 0 for every complex number z. Then in that case, we would know that 1 over p of z is entire, because certainly a polynomial is entire. And if it didn't have any zeros, then it's reciprocal. You'd never get zeros in the denominator, right? So that would be entire. And so what we're going to do is show that 1 over p of z actually is bounded, in which case it'll have to be constant, and we'll get our result immediately from that. So I'm going to have to ask you to remember something, which you probably won't remember, but you can go look it up. But in our previous lecture, or it was a much previous lecture, it was called Complex Numbers as Vectors. I had to go back and look and make sure that we did this. We actually showed that there has to exist some positive real number such that, and this was true for any polynomial, that 1 over p of z in modulus has to be less than 2 divided by the magnitude or the modulus of the leading coefficient times r to the n. And this is true when modulus of z is greater than r. So basically, outside of this disk centered at the origin of radius r, we know the function is bounded by this constant 2 over magnitude of a sub n times r to the n. But on the other hand, on the disk of radius r, which includes the boundary, which is closed and bounded set, f is continuous and so has an upper bound on the disk of radius r that includes the boundary. Yeah, this was a theorem way back in the section on continuity that said if a function's continuous on a closed and bounded set, then the modulus of the function actually has to attain a maximum value somewhere in that set. So at this point, we know that when we consider these two non-overlapping domains, that these two non-overlapping domains constitute the whole complex plane. There's the ones where z is greater than r. We have an upper bound on the function, on the modulus of the function there. And then we also have when z is less than or equal to r. Well, if you put those two together, you get the whole complex plane, and we have one bound on outside the disk and one bound on inside the disk. So the conclusion is the function's bounded on the whole complex plane. So 1 over p of z is bounded on C. And so at this point, we know 1 over p of z is entire, and 1 over p of z is bounded. And so Liouville's theorem tells us that this function is a constant. And of course, if 1 over p of z is constant, that tells us that p of z is constant. But hold on. A polynomial is not constant. That's easy to tell. So this is a contradiction. I mean, just think about it. Any polynomial, if you just let the modulus of the input value z go to infinity, then the modulus of the polynomial itself is going to go to infinity. That's just something you can argue with limits pretty easily. Polynomials are definitely not constant if their degree is 1 or larger. So, there you go. Proof of the fundamental theorem of algebra. We can actually extend, what the fundamental theorem of algebra says about polynomials. So the way the fundamental theorem of algebra was stated, it's just that, the polynomial has to have at least one zero. But actually, we know that if it's an nth degree polynomial, it's going to have n zeros. Some of them may be repeated, but it'll allow us to factor this thing. So let's go back to this polynomial. Let's call it p sub n to indicate that it's an nth degree polynomial. And then if it has a zero, let's say z1 is that zero, then it's a homework problem that I'll ask you to do a little later, that you can factor the polynomial as a product of an n minus first degree polynomial and then the linear factor z minus z1. But then you can apply the same reasoning to pn minus 1. Well, it's a polynomial of degree n minus 1. And so by the fundamental theorem of algebra, it must have a zero. So then you can, write that as pn minus 2 times z z1, or z minus z1 times z minus z2. Here z2 is a zero of pn minus 1. And then you can keep on doing this until you get it down to a first degree polynomial. So at some point, you'll get it factored down to something that looks like p times z minus z1 times z minus z2 times all the way up to z minus zn, where you have here n linear factors. If your polynomial is, defined over the real numbers, you can always factor it into a product of linear factors and quadratic factors. And so then if it's a complex one, those quadratic factors you can even factor down further into linear factors, which you kind of know from, the quadratic formula. If it turns up complex roots, they always come in conjugate pairs, and so then you get another pair of linear factors there. So anyway, When I think of the fundamental theorem of algebra, I really think of it this way. Like, it tells you that polynomials can be factored all the way down into n linear factors if it's an nth degree polynomial. The next result is a lemma that we're going to need to prove a bigger result called the Maximum Modulus Principle. This one is a little bit technical to prove, but I think we can fit the proof of it on roughly one page, so it's not so horrible. But here's what it says. It says that if the modulus of your function is less than this specific number, modulus of f of z naught, on a neighborhood of z naught of radius epsilon, and you know f is analytic on that neighborhood, then you can conclude that actually the function has to be constant, and the constant that it's equal to is f of z naught. And it's constant on that neighborhood. So it's kind of a Liouville-like theorem. Instead of it happening sort of on the whole plane, it's happening, we have this boundedness on a neighborhood, on an open neighborhood. But the result's sort of the same. We want to show the function's constant if it's analytic on this disk and it's bounded. But in this case, it's a little bit more specific in that we'll know what the constant value is. Okay, so how do we go about proving this one? So let's write down the hypotheses here. So let's suppose f of z is less than modulus of f of z naught. I guess that's just a less than or equal to. It doesn't have to be strictly less than. So suppose modulus of f is less than or equal to modulus of f of z naught on in z naught epsilon, where f is analytic. Then let's let z1 just be any old point in this neighborhood of z naught. And then let's let rho be the distance between z1 and z naught. Next, let's let c rho, always sounds like zero, but c rho, that's going to be the positively oriented circle mod z minus z naught equals rho. So this is centered at z naught of radius rho. Notice that it passes right through z1. All right, now here's what the Cauchy integral formula tells us. The Cauchy integral formula, I'm going to abbreviate that, tells us that f of z naught can be written as 1 over 2 pi I times the integral around c of f of z over z minus z naught dz. And the reason this is true is because our function was analytic on that neighborhood of z naught of radius epsilon, but this circle that we're looking at is strictly inside that neighborhood. So it's sort of like a concentric circle thing. Like here's z naught, and then you had this epsilon neighborhood around z naught, and then you had a circle that was setting inside of that. And so our function is analytic in and on that circle that's inside of our epsilon neighborhood. And we know that z naught is in that disk. It's at the center of it. So, we can apply the Cauchy integral formula. Let's consider a parameterization of that circle. So our parameterization of c rho will be z of theta equals z naught plus rho e to the I theta, where theta is going to run from 0 to 2 pi. So this is a parameterization of c rho. It's just a circle centered at z naught, right? So z naught, and then when you add that rho e to the I theta, that's the circle part of it. But adding z naught makes it be centered at z naught. So if we take what we know about from Cauchy's integral formula, so this f of z naught is equal to 1 over 2 pi I integral c rho f of z over z minus z naught dz. So if we write this, like use the parameterization, it becomes integral 0 to 2 pi. F of z would be f of z naught plus rho e to the I theta. And then if you do z minus z naught, the z that you're talking about is on that circle. So you'd get z naught plus rho e to the I theta. And then there's that minus z naught. So notice those z naughts cancel. And then dz would just be z prime of theta times d theta. So z prime is rho I e to the I theta, and then times d theta. And notice that you can simplify this down quite a bit. Like for example, I see a I cancels, the I that's setting outside of the integral in the denominator cancels with the I that's inside there. After you cancel those z naughts off, then that rho e to the I theta is going to cancel off. So all that stuff cancels off, and all you're left with is f of z naught plus rho e to the I theta d theta. So we have this new expression for what f of z naught is. F of z naught is equal to this integral, and this is what we want to make use of to prove our limit here. Actually, this is kind of an interesting integral if you look at it. I forgot the 1 over 2 pi out front though, so let me put that back in there. When you look at what this integral is doing, it's actually just calculating the average value of the function. The average value of a function is just the length of the, so you take the integral over the interval and then divide by the length of the interval. So anyway, from this we can actually get a bound on the modulus of f of z naught. The modulus of f of z naught has to be, well, equal to this 1 over 2 pi, integral 0 to 2 pi, f of z naught plus rho e to the I theta d theta. And you may remember a result. It came in the section just before we did contour integrals. It was about these. So the thing that we're looking at inside this modulus right now is not a contour integral. It's the sort of regular kind of integral that you evaluate by breaking it up into the real and imaginary components and then doing those two separate integrals in the components. And one of the results in that section said that when you take the modulus of such an integral, it will be less than if you pull the modulus inside the integral. So this is less than or equal to 1 over 2 pi, integral 0 to 2 pi, and then modulus of the stuff that's on the inside. We have modulus of f of z naught is less than this integral over here, okay? That's the main thing. I may want to give this a number. Let me call this inequality 1 here so I can reference it a little bit later. But remember, by hypothesis, modulus of f of z naught is greater than modulus of f of z, where z is any point inside that disk. So in particular, it's greater than f of z naught plus rho e to the I theta. So if you look at that integral from 0 to 2 pi of modulus of f of z naught plus rho e to the I theta d theta, well, we know that that's less than or equal to, just integrating the constant, modulus f of z naught. I mean, this is just a fact of real valued integrals, right? These are both real valued integrals, and the integrand of the one on the left is less than the integrand of the one on the right. But the one on the right, that's just a constant integrand, so that integral just evaluates out to the length of the interval, 2 pi, times the number that's inside there, f of z naught, or modulus of f of z naught. And so that tells you this inequality, well, maybe I should do it on the next line here. This tells me that modulus of f of z naught is bigger than or equal to 1 over 2 pi. So I'm just taking this previous inequality on the previous line and dividing through by 2 pi. And so I get this. Let's call that inequality 2. Well, I think if you look at inequalities 1 and 2, you can make a quick realization that if modulus of f of z naught is less than one thing, and then it's also greater than that same thing, it must be equal to that thing. So modulus of f of z naught actually has to be on the nose equal to 1 over 2 pi, integral 0 to 2 pi, modulus f of z naught, plus rho e to the I theta d theta. Okay. We can just rewrite that previous equation right there in the following form. Make sure I have enough modulus symbols here. So this integral is just equal to 0. Now if you focus on the integrand of this integral, first of all, it's positive, just because it's non-negative at least, okay? Non-negative. So you're integrating a non-negative function, a real valued function, by the way, and you're getting 0. Well, the only way you can integrate a non-negative function and you get 0 is if the thing that you're integrating is 0 to start with. So from there, we can conclude that modulus f of z naught, let's write it the other way around, modulus of f of z naught plus rho e to the I theta has to equal modulus of f of z naught. And this is true for any theta that's between 0 and 2 pi. See, this stuff that's inside the modulus on the left-hand side, right here, that's just what an arbitrary z on the circle c rho looks like, right? So what we're saying is that if your z is on c rho, then modulus of f of z equals modulus of f of z naught, a constant. But, you know, that circle, the only specification on it for rho was that basically rho was sufficiently sufficiently small so that that circle C rho stayed inside the neighborhood that we started with, but it could be any size that stays inside that neighborhood. So really what that tells you is that modulus of f of z equals modulus of f of z naught for every z inside that deleted neighborhood of z naught. But it's certainly true for z naught too, so I can get rid of the deleted thing. So, and I think that's what we wanted to prove, right? Yep. So that's sort of the technical lemma that we needed to get out of the way to prove the next big result, which is called the Maximum Modulus Principle. Okay, so here's what the Maximum Modulus Principle says. It says that if your function f is analytic and it's not constant on a domain D, then the modulus of that function has no maximum value in that domain. Remember, a domain is an open set, right? So what we know then is that there is no z naught in D such that the modulus of f of z is less than or equal to the modulus of f of z naught for every z in D. There may be some upper bound, but that upper bound won't be realized as one of the moduluses of a point inside of D. So it kind of tells you that, if a function is going to take on a maximum modulus somewhere, it's not going to be on the interior of that set. We'll see that as a corollary in a second. So let's look at a proof of this. The proof's kind of cool because it involves this sort of method that I think maybe we touched on once previously, and then there was a whole section that we ended up skipping, but it's called analytic continuation. Let's suppose to the contrary that modulus of f of z is less than or equal to modulus of f of z naught for some z naught in D and for all z in D. And what we're going to end up doing is getting a contradiction of the fact that f is non-constant. What we're going to do is just let's let p be an element of D, just be arbitrarily chosen. Only thing is I don't want p's not equal to z naught. Okay. Now because we've got a domain going here, that means that domains have this property that between any 2 points in the domain we can construct a polygonal arc that stays inside that set and connects those 2 points. So there exists a polygonal arc from z naught to p, which I'm going to start calling zn for convenience of counting. Well, let's say it this way. Polygonal arc from z naught to p. Give that polygonal arc a name. It's called L. There exists a polygonal arc L from z naught to p. So it's going to do something like this. It'll go z naught, z1, z2, zn, which is equal to p at the end there. So I don't know, I'm struggling to find a good notation for this, but the idea is we have a polygonal arc that starts at z naught, then it goes to z1, z2. Maybe a picture would be in order. Okay, something like that's going on. And then let's let D equal the minimum of all these distances, let's say between points Z and points W, where Z, let's say, is on this polygonal arc and W is on the boundary of D. And since this set is a domain, it's possible that it's the whole complex numbers and it doesn't have a domain. It doesn't have a boundary. So we'll just let D equal 1 if the domain is equal to the whole complex numbers. But otherwise, there's the set has a boundary, and we can measure the distance between all those points on that polygonal arc, and there's a minimum or an infimum of those distances. We can choose the z i's, the points on this polygonal arc, such that the distance between them, let's say between consecutive ones, zk and zk minus 1, is less than this d. Like if we had to, we could add some points in the interiors of these arcs, but we'd only need to add a finite number of them possibly to get the distance between the endpoints of these polygonal arcs to be less than this number d. So then we can consider neighborhoods of each of these points having radius d. Let's say n0 centered at the z0 of radius d, n1 centered at z1 of radius d. All of these are going to have the same radius, yada yada yada, all the way up to n sub n, which is centered at z sub n, the final point of radius d. So by choosing D the way we did and subdividing that arc up as needed, like what it has the effect of doing is that, like if you take Z naught here and you look at this disk of radius D around it, and then Z1 is going to have to also be inside that disk, and so then you make another disk around Z1, and then Z2 is going to have to be in that disk, and so on and so forth. If I put a disk around Z2, Z3 will have to be in that one. And this keeps on going until you get, to the end. Now here's Zn minus 1, and then Zn will have to be inside that disk. So the disks that are centered on these points that are on that polygonal arc are sort of for each adjacent one of those neighborhoods, they contain each other's centers. The reason for this is because, like, if you consider this first neighborhood around, Z naught, your function f is analytic there, right? And that previous lemma says that if your function f is analytic there and it's bounded, we did assume that our function was bounded on this whole domain. So it would be bounded, by this magnitude of f of z naught. So by the previous lemma, f of z would have to equal f of z naught for every z in this first neighborhood. But remember, z1, we know that that's in that first disk. So that tells you f of z naught equals f of z1. But then basically you can do the same argument now on that second disk. So by the previous lemma, we know that f of z equals f of z1 for every z in n1, the neighborhood of z1 of radius d. But we know z2 is in that next disk. So that tells me that f of z1 has to equal f of z2. And this just keeps on going until you get to the end. You'll have that, but zn is in the n minus 1, one of these things, neighborhoods. So that's going to tell me f of z n minus 1 equals f of zn. And so when you put all these together, f of z naught equals f of z1, f of z1 equals f of z2. Put all that together, you end up with f of z naught equals f of zn. And remember, zn was that arbitrary p that we just picked at the beginning. So if you kind of trace back what we did in this proof, I picked an arbitrary p at the beginning, right here, and the function value of that had to be f of z naught. So p was arbitrary in this domain, so f of z equals f of z naught for every z in the domain. And that finishes the proof of that. Because, well, I guess we need to point out we got a contradiction, right? This is a contradiction to f being non-constant. And that finishes the proof. All right. Well, there you go. Maximum modulus principle. And the following corollary comes off of the maximum modulus principle immediately. So it says if you got a continuous function f on a closed and bounded region R, and you know f is analytic on and non-constant on the interior of that region, then first of all, we know that the continuous function on this closed and bounded region R has to have, a maximum modulus somewhere that it attains somewhere in the set. But the maximum modulus principle guarantees that it can't happen on the interior. It happens, and it happens on the boundary and never in the interior. See, it can't be on the interior because if you took a point here, z in the interior, like in the picture I have there, if it's in the interior, you can put a disk around that point that stays entirely inside that set. But now your function's not constant on that disk, and it's analytic on that disk, so it can't have a maximum that occurs inside that disk, right? That was what the previous thing said. So, but that's true of every point on the interior, so that means there can never be a maximum that occurs anywhere on the interior of the set. It can only appear on the boundary. But it has to appear somewhere, so it definitely is on the boundary. So that's the proof without writing any of the details down. So this next example is kind of cute. It gives you kind of a instance where you can see how the maximum modulus principle is coming into play. So consider this function f of z equals z plus 1 quantity squared, and I'm defining it on this triangle that I've drawn in yellow here. Then you could ask, where in the region does the modulus of f of z have its maximum and minimum values? Now we know, according to the maximum modulus principles corollary up here, that this function is definitely continuous everywhere. It's analytic everywhere, so it certainly applies to this yellow region here. So the previous corollary says that this thing has to have a maximum, and it's got to be on the boundary of this thing. Where? Well, actually, you can see it geometrically pretty easy. If you would let d equal sort of the difference between the distance between an arbitrary point z and the point -1. So this is a function of z, so d of z, where z is in this, let me give this region here name r. And if I look at the square of that function, so I'm looking at the modulus squared, so d squared of z is modulus of z plus 1 squared. Notice that that's exactly the modulus of the function that we started with, f of z. But geometrically, we see that that distance function d takes a maximum. Like what we're just measuring the distance from this point -1 here in green, the green dot. We're just measuring the distance between that fixed green dot to points z in that yellow region. Well, you can see geometrically what's the maximum of that. It happens whenever the z is equal to 2, that farthest corner from -1. And it takes the minimum at z equals 0. So that means that d squared takes those same maximum and minimums, or has the maximum and minimums at those same places. Just point out, where are those points with respect to that region? They're on the boundary, of course. So, all right. I think I will stop there. Talk to you again soon. Bye.